Okay, let's just dive right into this explainer. We're going to completely demystify the massive, complex infrastructure of hydroelectric dams, and we're going to do it by following the fascinating journey of a single drop of water. We so often just flip a light switch and totally take the resulting electricity for granted, right? But the sheer architecture required to harness the raw, chaotic power of nature, it is absolutely an engineering marvel. So today we're breaking down the anatomy of a hydroelectric project, step by step, to really understand how the whole shebang comes together. But before we zoom in on the microscopic parts, we really need to appreciate the sheer scale of the system layout. It's basically an entire flow mapped out right against a mountainous landscape. It starts way up top at the massive reservoir, funnels all the way down through the mountain, passes right into the powerhouse, and finally pushes out to the electrical grid. It's just this beautiful, unified visualization of three distinct phases: the flow of the water, the conversion into power, and the final delivery to the grid. So here's our roadmap for this journey. First up, controlling the water source. Then the downward conveyance journey, converting that water to power, delivering electricity to consumers, and finally wrapping up with system design and efficiency. At a macro level, it all boils down to these 5 steps. We have to store and regulate the water, convey it safely downward, convert its energy, discharge the water safely back into the river, and then deliver that electricity. Just think of these 5 functions as our mental scaffolding as we explore the physical structures. Section 1. Controlling the water source. We're starting way high up upstream, where rivers, lakes, or seasonal snowmelt give us our initial water source. To harness water, we first have to command it, right? And the reservoir is absolutely crucial here. It stores the water to give us the required hydraulic head, which is basically just engineer speak for the vertical drop that we need. Plus, it regulates the flow, so we actually have reliable power generation year-round. But holding back an entire valley of water, that requires the dam. The dam impounds the water across the river valley to create that storage, and it is heavily engineered to resist immense hydrostatic pressure and uplift forces. It is literally the physical anchor of the entire project. But as we all know, nature is incredibly unpredictable, and sometimes there's just way too much water. That's where the spillway steps in. It really acts as our first structural hero, providing a safe passage for excess floodwater to completely bypass the dam, which protects the core structure itself. Whether it's an OG, chute, side channel, or shaft design, the spillway is what ensures the dam actually survives the incredibly destructive forces of a major flood event. Section 2. The downward conveyance journey. Now we're following the water as it enters the intake structure, which regulates its entry and uses things like trash racks and intake gates to stop any floating debris from getting in as we start moving downward. Before the water goes any further, though, it has to be cleaned up. It passes through this really clever area called a desilting basin, where the water's velocity is intentionally slowed down. This allows silt, sand, and suspended particles to just naturally settle to the bottom. Trapping all that abrasive sand early on, that saves the ridiculously expensive turbine machinery downstream from severe wear and tear, dramatically improving both the lifespan and the overall efficiency of the plant. Moving further along, we find the forebay tank and the surge tank, which, honestly, solve a massive engineering problem. Just think about it for a second. You've got thousands of tons of water rushing downward. If the turbine's electrical load suddenly drops and the valves have to close quickly, well, all that water still has to go somewhere. The surge tank absorbs that violent pressure spike, a phenomenon known as water hammer, by giving the water a place to safely surge upwards. It effectively stops those massive pipes from literally bursting under the strain. Safely past the surge tank, the water takes a steep drop into the penstock. This is a high-pressure welded steel pipeline that conveys the water directly to the turbine. Because of the unbelievable weight of all that water stacked up above it, it has to be designed to withstand up to 20 to 30 bar of pressure, depending on the specific site. And right at the very end, it's isolated by the main inlet valve, usually this massive butterfly valve that controls the water flow to the turbine. This is absolutely essential for safe operation and maintenance down the line. Section 3. Converting water to power. We have finally reached the bottom of the drop, arriving at the powerhouse and the turbine itself, where the physical momentum of the water formally becomes mechanical rotation. So, the water hits those turbine blades with incredible force, rapidly spinning the generator. But the brilliant engineering doesn't just stop once the turbine is spinning. After the water violently turns the turbine, it enters what's called the draft tube. This is a specially shaped diffuser that serves a super vital role by recovering kinetic energy. It actually converts the remaining velocity of the water back into pressure head, which maximizes the turbine's efficiency right before the water is finally discharged. The water's physical journey through our giant machine concludes at the tail race channel. Its main job is to just convey the water safely back into the natural downstream river ecosystem. And it's carefully designed to do this with minimal backwater effect on the turbine and to prevent any erosion of the riverbanks. It basically ensures a gentle, sustainable return to nature for our water drop. Section 4, delivering electricity to consumers. While the water itself is returning to nature, its extracted energy is embarking on a completely different, high-speed journey out to the power grid. Before that power can travel miles and miles across the country, it hits the step-up transformer. To make this journey economically and efficiently, the transformer massively boosts the generator's voltage. For instance, it might step it up from 11 kilovolts all the way to 132 kilovolts, or even 22 to 400 kilovolts. Now, why do we do this? Well, drastically increasing the voltage reduces the current, which in turn minimizes what engineers call I²R losses, which is basically just power lost as heat over those long-distance transmission lines. Next up is the switchyard. This area handles the switching, protection, metering, and overall control of all this heavy-duty electrical equipment. The switchyard acts like a traffic cop, routing the flow and sending electricity out across the transmission lines at staggering typical voltages. We're talking 132, 220, 400, or sometimes even up to 765 kilovolts. This massive infrastructure is what guarantees the reliable, continuous delivery of clean electricity straight into the grid and eventually right to your home. Section 5, System Design and Efficiency. Now, let's take a quick look at the typical design data to truly understand the macroscopic scale, scope, and performance of the systems we just explored. Remember when we talked about the hydraulic head earlier? Well, the vertical distance the water falls from the reservoir down to the turbine can be anywhere from a relatively modest 10-meter drop to a massive gravity-fueled plunge of well over 1,000 meters. It's a simple rule. The greater the head, the greater the pressure, and generally, the more power you can extract from a given volume of water. Because of that incredible drop and discharges that can range from 1 to 10,000 cubic meters per second, the power output is wonderfully scalable. A single project's output can range from a localized 100 kilowatts to a staggering 3,000 plus megawatts for one of those massive grid-anchoring dams. Generally speaking, these operate with a plant factor of about 30 to 60%, heavily depending on the seasonal availability of water. Now, these numbers right here reveal exactly why hydroelectricity is so vital to our overall energy mix. It operates at an absolutely astounding 80 to 92% overall efficiency rate. When you compare that to traditional thermal power plants, which lose a massive amount of energy just as waste heat, hydro's ability to convert raw water energy into electrical energy is almost entirely unmatched in large-scale power generation. But in order to maintain that incredible efficiency over a long service life, these projects have to be deeply respectful of their environment. They're designed against super strict codes and specific seismic and hydrological conditions. Crucially, operators have to rigorously manage sediment to prevent wear and tear, and they must strictly adhere to environmental norms. This ensures an adequate environmental flow of water is constantly being released to sustain the health of the downstream river ecosystem. Which really leaves us with a critical question to ponder. With up to 92% efficiency, hydroelectricity is undeniably an incredibly powerful, clean resource. But as our global climate changes, fundamentally altering seasonal snowmelts and river flows, how are we going to adapt? How will we engineer the water sources of tomorrow to keep these structural marvels running and our grid alive? It's definitely a complex challenge for the next generation of engineers to tackle. Thank you so much for walking through this incredible journey of a water drop with me today.